Hello everyone, I'm Keguang He from China Mobile. I'm a software architect at China Mobile, and I'm also have 4-year experience working for ONAP. Today, it's my honor to have this presentation here. Guanyu Zhu from Huawei, expert from Huawei, we will give the presentation together. Our topic is about intent-based incident management in ONAP. I hope at the end of this presentation, you can have a better understanding about general intent implement solutions and several detailed use cases in ONAP. First I will give a brief introduction about intent-based network. And from TM Forum's definition, intent is a formal specification of all expectations, including requirements, goals, and constraints given to a technical system. And the intent can directly originate from human. For example, custom expert the system to utilize the underlying infrastructure. And the intent also arises within the autonomous system using between subsystems. And in my opinion, intent is a master for autonomous network, and intent evaluation of autonomous domain interface and the interface between autonomous domains has evolved from rule-based, policy-based to intent-based. And the intent define what autonomous domain is expected to achieve, leaves the details of how to design and operate the network to the insight to the internal operation of autonomous domain. And the intent also is a key technologies of closed loop management. Some still have intent-related project for several years, like RTF, ENI, ETSI ENI, ETSI NFV, ETSZM, TM Forum, and 3GPP, and CCSA. And our team conduct deeper research in intent-based network for several years. We research the intent use case, intent model, and intent management of autonomous network. And we try to improve interoperability between component systems via standard intent description. And we try to make all intents, especially machine-to-machine intents in the system, operate in the same way, and decompose the complex intent into sub-intents of different dimensions. Support use case related to intents to demonstrate our requirements. And our team also leading intent-related standards in several standard organizations. In ETSI ENI, we are the report of ENI R13. And in ETSI NFV, we are the report of IFA R50. And we actively contribute to 3GPP SA5, release 7 and 17 and release 18. We also actively contribute to autonomous network and intent project in TM Forum. And in CCSA, TC7 and SP1, we lead 5 intent-related projects. We also designed the intent management architecture of autonomous network. For autonomous network, they have 4 lines. From bottom to top, we have network element layer, network layer, service layer, and business layer. And from this picture, you can see there have 2 reference points. The first type reference points is the interactor between the intent manager function of the intent owner and the intent manager function of the intent handler. The second type reference points is the intent management function local interacts with the intent manager function global. And they have several interfaces to support the reference points. We have create, update, delete, query, and report those mandatory interface. We also have two optional interface. Probable interface explore whether the intent handler can achieve a specific intent. And negotiation, intent owner negotiate with the intent handler on the modification of intent permits. We also give intent management function architecture. We divided the intent manager function into two parts. The first part is the intent manager function local. It is responsible for recognizing the input intent and the system state, and make decisions on the actions to be taken based on cognitive results. And the intent manager function global includes intent ability management and the corresponding database. We also designed end-to-end intent processing. For intent instance, it will have several different stages, like acknowledged, compliant, fulfilled, degraded, fulfillment failed, terminate. And different stages can transmission to each other according to different situation. We try to determine the interaction process between intent manager function and other related function, and standardize the definition of intent lifecycle management. We also design a general intent model. It includes several classes like intent instance, intent report, fulfillment, intent object, and intent expectation object, expectation targets, and context and conditions. We will try to provide a specific general structure, vocabulary, semantics, and mechanism, and try to ensure unambiguous expression and machine readability. We are not only do research in standard organizations, but also we develop several open source practice in ONAP. This is intent project top level where in ONAP. We have several components to support the internet-related worker, like UI, NRP server, and internet manager functions. We use those components to achieve end-to-end intent processing. We provide a general intent interface, general intent model, and the NRP server supports man-to-machine intent, and the intent manager function implements machine-to-machine intent. Achieve end-to-end intent through layer by layer decompositions. In order to support our concept, we develop some new components in UX UI. First, we add a new input manner, intent format input. Users can input formatted intent from here. And we also add a new microservice, intent analysis server. These servers provide a general intent model and intent interface, and provide intent translation based on AI ability. Also include intent decomposition, intent orchestration, intent report, intent lifecycle management, and intent-based closed-loop management. Users can import their formatted intent from intent formatting input, and then intent analysis server will analyze those requirements and translate those requirements into different actions. Then communicate with the other components in ONAP, like SO, DCAE policy, to implement end-to-end intents. And in ONAP, we have three important requirements. The first requirement provide a general intent model and a general intent interface to ensure that all intents, especially machine-to-machine intents, operate according to the same expression and process. And the second requirements are optimize the internet interaction process, introduce AI-related technologies, and implement more interfaces such as the internet report. And for the third requirements, Guanyu will give more detailed information about these requirements later. And based on our hard working, we get some achievements from ONAP. The general intent model and the general intent interface requirements win the top achieve award, and the user case UI project wins the S3P improvements. In this page, I will give an introduction about the general intent model and the general intent interface use case. Operators provide intent-based cloud-list line service and provide increased bounding assurance measures based on user requirements. And their user want to configure a cloud-list line with bandwidth of 1G, and they also want to have a exclusive assurance. So we divided the users' requirements into two expectation: delivery expectation and exclusive assurance expectation, and use our general intent model and general interface to translate those requirements into detailed actions via SO and DCAE components. And from this picture, you can see you can monitor the bandwidth parameters. The bandwidth value automatically changed according to different situation to fulfill the user's intent. Okay, in the future, we will continuously conducting IBM research. We try to use LLM to make the system more accurately understand about the user's intents. We also try to implement intent verification and improve intent interaction to implement end-to-end intent closed-loop assurance. And we continuously collaborating with other SDOs like TM Forum, CCSC, 3GPP, ETSI. And I hope if you are interested in intent-related technologies, you can contact us. We can do some wonderful contributions to standard and open source organizations together. Okay, that's all for my introduction. And next, Guanyu will give a more detailed introduction about the use case.
Thank you, Keguang, for your wonderful speech. And then I will present over the small part of the rest. This is Zhu Guanyu, and from Huawei's Clarified Networking OSD team. We have cooperated a lot on the intent-based network. This is an IBM project. Since release 11, we have jointly developed the common intent model and common intent interface. In addition, the intention exchange process is optimized in release 12. And in future, release 13 and release 14, new features will be continuously enhanced. In release 13, the incident management technology is introduced to improve intent reporting and the intent loop process, especially the scenario where the intent creation fails, such as incident occurs. Currently, we are in the development process, and we expect to produce the first demo in November this year and release the next version, the release 14 in the first half of next year. Before we talk about the intelligent incident management, let's talk about the traditional ones. This is the traditional incident scenario. A device of operator is faulty and no alarms is received. After service are interrupted for more than 2 hours, ONM personnel receive a complaint from the operator and start incident locating. The incident cause cannot be found after traditional methods such as viewing alarms and traffic information. And finally, the key information is extracted from the running indicators of the NE bottom layer and the conclusion of hardware incident is drawn. The entire incident process, the entire incident process interrupts the service of more than 6,000 users and more than 10 experts and involved in the analysis, which takes more than 7 hours. And we can know that the traditional intent management is very limited. First, sorry, wait a minute. I can't find my can't find my mouse. Okay. Oh, sorry. That's back. First, it can detect incidents in limited dimensions. It mainly relies on information such as alarms and traffic routes and cannot come over incident scenarios. There is no effective method to detect hardware forwarding, configuration, and protocol exceptions. Second, it cannot proactively prevent potential problems. Most potential problems miss the early check window. Incidents can be detected only after services are affected and operators' feedback is received. In addition, there are few efficient methods for locating incidents. Once an accident occurs, our only choice is to check the massive ONM data one by one and view traffic changes and NE logs. This process is inefficient and prolongs the impact of failure on our service. But these problems can be improved by intelligent incident management. Incident management introduced the AI algorithm and self-created streaming framework through clustering and root cause identification, the focus on directive incidents is reduced. This greatly optimizes and the incident detection and management process significantly improves the efficiency and implements multi-level incident detection and intelligence diagnosis, thereby improving ONM efficiency. In the incident detection phase, repeat alarms can be clustered and compressed in real time with online training and incremental learning of live network data. The algorithm model can gradually identify unknown incidents and uncertain problems. In the incident diagnosis phase, the knowledge base and AI algorithm are used to provide troubleshooting suggestions for root causes of incidents, lowering the OM threshold. And not only the more intelligence, but also complying with TM4Os and IETF standards. This ensures the interoperability and the scalability of system and support future service development while meeting meeting occurred service requirements. Business requirements and standards requirements are driving the introduction of incident management. And with the development of our infrastructures, the system become larger and larger. The increasing of server quantity and complexity, the management system may be overwhelmed by the frequency and quantity of various alarms and information, which may reduce the processing efficiency, difficult to identify root causes and repeat tickets. And incidents are actually unexpected interruptions of network services or detections of network service quality, which are clusters from the above information. We can see the layer and layer. It use some filtering, association, and clustering, and some algorithm to compress the alarms and other informations to incident. If technical details are shared, the upstream and downstream relationships of incident management can be displayed like the picture. The incident management collects the information about various bottom layer NEs from the southbound interface, and the analysis and diagnosis actions are triggered by service requests from the northbound interface. It provides consistent management of different types of data which comply with TM4 standard and the service impact analysis model of incident management can be used to identify the relationship between incident and network services. Incident corresponds to one or more network services. The relationships can be pre-configured in the system or dynamically identified. There's some applications. The first two cases involve the function of pre-configuring the relationship between service and incidents, and the third use case is about the dynamically identify the relationship and report the root causes. In application, incident management can reduce the number of tickets by 33% and involve the tickets efficiency by 10%. We hope to build the better and more standard incident management system in the telecom field, combining with IBM in ONAP will be our new practice. And if you have any question, you can contact me and Keguang by email, and can also discuss here. And, any question? Thank you.